The normal approximation is so straightforward to implement that it's very tempting to use it whenever you get the chance. You've got a mean, a standard deviation, let's do a normal approximation. Well, that's fine, but as we know, not all data are normal. So here's our maternal age data. It would be really silly to put a normal curve on that. So it is well worth remembering that not all data are normal, not even approximately normal, and we have to resist the temptation to use the normal approximation just because we have a mean NSD and some data. Sometimes you can see, even via just the mean NSD, without the histogram, that the data cannot possibly be normal. So a typical example is you look at rents in a neighborhood and they have an average of 900 and an SD of 600, and you ask yourself, could this distribution be approximately normal? Well, we have an SD of 600 and an average of 900. If you go 1 SD below average, you're at 300. If you go 2 SDs below average, well, that's 900 minus 1200, and suddenly your so-called rent is negative. Is the landlord paying you to stay there? I don't think so. 2 SDs below average, you have nonsense for your variable. Your variable is blocked at 0. It cannot get below 0. And so what you note is that the rents can't go 2 standard deviations below average, but the normal curve certainly can. It has 2.5% of the area below 2 standard deviations. That left-hand tail has 2.5% of the area. And so how do we put these two together? The normal curve has to have 2.5% below 2 SDs. The rents cannot go below 2 SDs, so now what? Well, that means the rents aren't approximately normal. And we just have to live with that. We can't will them to be normal. One of the things that you ask yourself is, how can the SD be so big? Well, the rents are going to be non-negative. They have an average of 900. A huge SD must be coming from the right-hand side because it can't come from the left. So it is most likely coming from a long right-hand tail. This is no surprise because rent, any distribution of things that involve money. There are a few individuals who pay lots and lots of money or who have lots and lots of money. This is not atypical. And so it's not unreasonable to think it might be coming from a long right-hand tail. Though of course you can't be absolutely certain until you've looked at the data. The point is that comparing this average of 900 to this average of 600 in a non-negative variable, you know the variable can't be approximately normal. So if it's not approximately normal, then what can you say about it? You still have Chebychev. Chebychev's bound always works. No matter what the distribution, doesn't matter how awful the shape, at most 1 over k squared of the data can be outside the range average plus or minus k SDs. You've known this for some time, and it is a good thing to resort to when you have no idea about the shape of the distribution. Now, of course, it's a bound. It's not an approximation, so you're saying at most 1 over k squared. You're not saying 1 over k squared or even approximately 1 over k squared. That's unsettling to people because people want an answer. Roughly how much is it? Well, if you don't know the shape of the distribution, that's all you can say. And it is better to have the correct bound than to have a poor approximation. Because if I say that my distribution of maternal ages is approximately normal, I can go away and calculate to my heart's content, but it's not approximately normal, so my approximations are only as good as their assumption, which is bad in that case. So the moral of this story is, the normal approximation is beautiful and simple, but it should be used with extreme caution.